It's so good to see everybody here at 8:06. We're getting more and more prompt for our ground rules. And Fred just uploaded a PDF file of some definitions. Maybe we'll look at that after we get going here to get started. He wants that to be a matter of record. We're all here rolling, and that's exciting to see everybody here. Richard, how are you feeling, and what do you anticipate to get from today's call?
I'm feeling pretty good. We're back from a week and some with our daughter in British Columbia, and she's doing pretty well and keeping herself busy. So I think there will be a downtime at some point. Um, but anyway, feeling good that we were able to be out there and be with her and her sister being there as well.
Oh, good.
Uh, so that's all good. And she's been up island doing some more book readings of her new novel and surrounded by friends and having a spa and doing all kinds of things for herself as well as what she has to do as an executor and grieve the loss of her husband and do all the admin work that's associated with what has to be done now. So I'm looking forward to being reconnected and a little bit more focused on the fuller explanation and what we've been reading. So, Manu, how are you feeling? What's your expectation for uh, the session today?
Good morning, just feeling good. My expectation is that we continue and then we look for applications and then we'll be more tolerant with each other. Um, Fred, how do you feel? What do you expect?
Thank you, Manu. I like the high energy of the call. It's started with a bang, and I hope it's going to keep going like this. Everybody's on time. And I've worked out the dissonance introduced last Wednesday by the reading of that chapter on that other book we studied. And I've chanted my little songs to Galileo. And so I'm all cleared and ready to go. I hope I can learn something a little bit today. Either it is what Manu has suggested he would prepare for this week and share with us to enlighten us, or we keep going with the book. In either case, I hope I can learn something and be happy to hang out with you guys. So, Joe, how are you feeling today, and what is your takeaway? What is your desired takeaway?
I'm feeling pretty good. It's great to be here. And I'm just looking forward to kind of building off, some of the conversations that we had last week. And I appreciate Manu actually having, kind of, shared some things with me regarding the hexagon as well, and as well as the Pentagon. So yeah, I mean it was a lively discussion last week, and I agree. There's a lot of good energy on the call, and it's good to see everybody. Lee, how are you feeling? What would you like to take away from today?
I'm feeling very good. Last night I danced my heart out.
Nice.
We went to a place called Lake Effect, um, a bar restaurant, and a fabulous band that was playing. Happens to be a friend of Steve's, and just danced my heart out. And I'm feeling the pain. I really am. But after we left the place well, it was this afternoon, Steve took me and bought these because my feet are always very cold. I have my blanket, my sweater, my turtleneck on. I'm warm from here up, and my feet were always cold, and now they're warm and toasty. And I'm ready to learn more than I have ever known. And I appreciate all of you. And I turn it over to Steve.
How's your sugar really quickly?
Oh, very high. Very, very, very high. We went and had a hot dog at Costco, and that was the wrong thing to do.
But they're so good.
Oh, there, and we figured out Steve had to calculate all of the carbs, and I took the insulin for it, but it still hasn't started coming down, so it's way up high. So hopefully it won't last, and I'll get it together soon. I just checked on it, and it's still 400.
Jesus.
Oh, look.
He wanted to
Fred,
say
who
hello.
is your guest? What's his name?
Julia.
Julia. So it's a
Julia.
she.
Yes.
Julia.
What's her takeaway gonna be?
My takeaway with her is that when you have silence is good, but when you have a minute order, silence is very, very suspicious.
She's
Yeah.
beautiful.
Thank you.
Thanks for sharing. I'll get you. Okay, good. Thanks for sharing your new friend there. Already, my blood pressure immediately went down as soon as I saw the dog.
Yeah, me too.
I got calmer already because I was all jacked up because prior to starting the recording, I reminisced about last week and how I had Italian neighbors whom I hadn't thought about since 1959. And the fact that I remember that neighborhood so well and everything. Okay, good. So I'm all excited. I think just when I think I understand some of this stuff about tetrahedrons and the isotropic vector matrix, I read another chapter and find out there was more to the story than I thought was possible. My brain is not as topological as Manu's, and so I struggle with things. Well, I'm looking forward to our conversation today. I think we left off on page 240 last week at figure 14-9. And however, Fred did some research and put together a paper on duality in the context of Buckminster Fuller. And so I think it would be good to review all that. So I'm going to go for it, and we'll go through it and see what.
It's actually the version of your looking up, asking AI to give us more distinctions about duality that I put together. It's just I just added some formatting on what was in the chat last week. So we've been through that. I just thought it would be a good reference document for everybody to have.
Well, and as I read through it, Fred, it seemed to me that there was some wording here that I hadn't heard yet still, or at least had not landed very significantly in my cerebral cortex. So I'd like to review this. If everybody's open for this, I'd like to go through this. One, it reaffirms the work Fred did, but number two, I'm going to get some exposure to some ideas that my brain keeps trying to simplify what's going on, and I don't think there's any way to do. I think it's better to see the broader context. So Manu has his hand up, so maybe we'll wait and see what Manu wants to share. Go ahead, Manu. What do you got in mind?
No, I just wanted to go through what I promised last week, and then
Okay.
put it aside quickly.
Why don't we do that? Because you promised it last week, and we were all looking forward to your summary. So do
Okay.
that, and then maybe go ahead.
I want to share my screen here. Where do I go? Share screen.
Yes.
Share. Uh, Do you all see my screen?
Yes.
Yeah.
Yes.
Do you see that?
Mhm.
Okay. That is you can see in there, do you all see the pentagon on that?
Yes.
Yes.
And do you see the hexagon?
Yeah.
Yeah. The hexagon's a little bit, you have to kind of strain to see the pentagon and the hexagon, but that's cool. I think I see the hexagon too.
Okay. So that's the way it is. I think
I don't see the Pentagon.
Aha.
there is the pentagon. Do you see
Yes, we see your marker.
Yeah,
Whoops.
that's it.
what
Whoops.
happened?
You
Okay.
just went away. You want to click on that first picture again.
Okay, I see it.
Uh,
I see it on the top right picture, the small top right picture. I got it. Thank you. Yes, this one.
That's where the pentagon is. Where's the
Okay.
hexagon?
Yes.
And I see the
key-
hexagon also.
Yeah.
You see the
The-
hexagon?
Yes. I
I
mean,
don't
not on
see the
that
hexagon.
not on that picture, but I saw the hexagon on the other one.
Well, I thought I
You
did.
see on this one?
Yes.
Okay, let me go different
1, 2,
pictures.
3, 4, 5, 6. Yep, I see the hexagon.
Yeah.
It's a hexagon.
It's a
Do you
six-sided.
see
It's a
do you see the
six-sided
pentagon?
polyhedron.
Do you see the pentagon now?
Yes, we
Yes.
see the pentagon.
Okay.
Lee, do you see the pentagon? Right there?
Which has
5 sides. It's a two-dimensional polyhedron with 5 sides.
There. Do you see my cursor?
Yeah.
Okay.
And go
Yeah.
back to the 6. Because the 6
Which
is,
one?
you have to smash that thing into 2 dimensions. Go back to your first slide, please. Yeah.
Yes.
So 1, 2, 3, 4, 5, 6, but you have to smash that sucker. You have to forget about the pentagon and smash it to C6.
Do you see the three axes of symmetry before? You see that?
The 3
And I put
axes
them.
of symmetry.
Yep. Okay, look at that contour. Look at what is round and what is sharp, pointed. You see one here, 2 here, and 3 there.
Yeah.
And they all alternate. So on each, for example, here, if I call this positive, that one will be negative.
If you call what positive?
If I mark this one, the one that is like a inverted U as positive, is opposite here will be negative. This one that is pointed. And same. I use how do you call it? Dental floss. Dental floss toothpick. I just cut them, and I use the pressed it to put. I didn't want to damage my map. Okay. So
I
if I
don't
go,
see, I see the symmetry in the pentagon, but I don't see, I mean, I've got to flatten that thing out to see the hexagon. I don't,
okay,
yeah.
hold on. I'll show you all of these different images first, and
Okay.
then we can understand.
Okay.
That's the second one. If you look, the hexagon, I've numbered the edges of the hexagon. Okay. Do you see that? We've gone through round. Okay. The key is that you zigzag on edges. It's not on a plane. You zigzag like that. Let me show you a zigzag that is clean for you to see. You see that zigzag? 1 and 6.
Yes, I see the zigzag.
Yes. So you go around, you go deep, high, deep, high, deep, high, deep, high. It's like if you were crossing the equator. Okay, so that is it. And then if you look at that, if you project now this thing on a plane in 2D, then you have the pentagon and the hexagon in the plane with different angles. So that is the concept of the boundary. And then if you look at the boundary here, I will explain because I don't know if this one is clear for everybody. Okay.
We
Now,
don't know
if I come
which one is clear for everybody.
the pentagon in the hexagon, the pentagon and the hexagon in the circle on a 2D.
On a 2D plane, yeah.
Yes. Now let me explain what I've come to define as fiery and pyre. I think that was another question that Fred asked. Am I right, Fred?
Yeah.
Yes, it is correct.
Okay. Let's go here now. Let's go to where I can see this. Okay. If you look at this, for example, I hope the contour appear here. You see, this is about this, if you look at my cursor, it's defining the boundary of this polygon here.
Which is the hexagon.
Yes,
Yeah.
it can be exactly, it's the views. I see it. It could, this thing, if I look at the face like that, it could be a pentagon. It depends on where I'm looking. Now, if you want to make a calculation of this, you see here that I have a closed triangle, triangle, triangle. I can precisely calculate what is here.
You mean the surface?
I'm talking about is enclosed. It's a closed domain.
Yeah, but what are you calculating?
No, whatever. Let's say, for example, a surface, or if you were a 3D figure, a volume, I would do. But in this case, I'm studying the effect of the exchange between the inside and the outside of the whole of this body. If you look at it, whatever is inside here can be well circumscribed with polynomial equations that have a solution. You can take, if I start from this point, for example, I take a turn here at this point, that is 1 dimension already, 2 here, 3, 4, 5, etc. I have dimensions as the terms. But what is important here is that to see all of this, I don't need all of the 6 terms. I need 4 terms to define it. But with that, whatever the case, whatever a million terms that you take, you can circumscribe that into an equation in the form of the sum of scalar coefficient and the x, or the distance, exponent something.
You said scalar coefficient?
Yeah, a polynomial equation, the way you write it is a x0 plus b x1 plus c x3 plus d x4 plus etc., etc. So when you write that in that form, it will have a solution because it closes. And that solution is in the form of a phi expression. If you look at it, the solution, you will be approaching it by as Steve would say, how do you call it, Steve? As your daddy used to tell you about the story of going to the moon. Continual adjustment.
I called it successive reapproximation. That's what my stepdad called it.
Exact. A successful reapproximation is that series of polygons of different order that you do in order to get to something that is finite. But if I want to study the effect, for example, or what comes here and goes. I cannot calculate it. What comes onto this surface? Let me take a second surface here. Imagine an exchange. And I'm looking at what comes in when things come here, that when it hits, let's say Australia here, when it hits Australia, some goes in and some is reflected. How do I calculate what is reflected? I can calculate finally what is inside. What is reflected, I cannot calculate it. The only way for me to calculate it is to imagine another sphere that is around there, and that is divergent now. Anyway, and assume that that went into that sphere, but it's no more in my original sphere. And in order to do that, you need to use a transcendental number. And I
What's a
generalize that
transit?
a transcendental number is an irrational number which is not a solution of a polynomial equation, as I said. Like pi, you know the expression pi.
It does not have an algebraic expression of it.
Yes.
Oh.
So it has to be something invoked from outside my domain that I call transcendental. And the most common transcendental that we know is pi. 3.14. But there are many others. There is E, for example. That is the base of what you call the Neperian whatever. You know, when you calculate the log, the base, you can't. In order for you to calculate the log, you have to fix something that is transcendental to your system of thinking. There are many others. Is a few of them, but those are the two most known.
I'm gonna just invite you to pause for so Lee and remind myself something, and then you're gonna have to share your screen again.
You're muted, Steve. You're muted, Steve.
Okay, good. Thank you. So what I'm going to do is interrupt your sharing just for a second. I'm going to show Lee this phi and pi transcendental thing from our cosmometry discussion. So here is everything inside of this circle that radiates out. This is the head. This is the North Pole.
We're not seeing, Steve. We're not seeing anything.
It'll be there in a second.
Yeah, that's it.
So this is a torus. This is the North Pole or the South Pole of the torus. And this is the equator. So we're looking top down or bottom up on the torus. Everything inside of the torus is a phi manifestation, and outside of it is pi. These are transcendental. This is the 3.1416. This is 1.614, whatever. But everything outside the circle is transcendental. It transcends the awareness or our experience here. So this is a pi calculation. This is a phi calculation. Transcendental, it's outside of, I guess you could say this, pi is convex. Could you say that? And phi is concave?
Yes.
Is that like,
it is.
Circles relevant. I don't know.
What?
Phi is used in calculation of things that are concave. We can only count what is concave.
Right.
Because it accumulates. That's another why you use the logarithm expressions. Because logarithm is a mathematical translation of accumulation of things.
Okay, so
that's why it goes.
That's why it goes what, Manu?
That's why the logarithm flattens. You see, the exponential goes wherever it goes.
It goes out. Exponential goes out. It's convex.
Yes.
It's outside.
And logarithm is a natural organic process that accumulates. You have a mass. For example, let's say a filtration system. You're taking out all of those things that you are accumulating somewhere and accumulate to a certain level, it will break whatever that is in there. So it is logarithmically accumulative, and it does this.
Okay.
That's why the logarithm is so apt at describing organic and natural. Yes, Fred.
I think Lee has her hand first up.
Pi is infinity. It goes out to infinity. Phi goes, there's no infinity, it just is within itself. Is that what it means?
Okay, yes, but infinity, Lee, you
Yeah.
have to specify what you call infinity, because infinity in our conception, in the way I understand it, is something that disappears and come back from where I'm thinking.
Mm-hmm.
That's why you have the notation of infinity is two ciphers that are like this.
Oh, okay.
That's the way the symbol of infinity is two ciphers. It goes like that.
And continues
So
for
if yes,
infinity.
yes, and it has to do with, if you take, for example, two wheels that are turning like that. Counter. Say you are pumping water. You know the way you pump water. You have two dented wheels that are turning. One is turning that way. The other one counterclockwise. If you see on the plane, and it will carry the water inside and splash it out. That water goes round and comes back, for example.
I always thought infinity could go forever, like a mirror in front of you and in back of you, and it just goes and continues.
Yes, yes.
Yeah.
But it is actually a cycle that you don't see, because
That's
it
like
goes and
that's
comes back.
self-reference.
Yeah. Universe is finite. It's the manifestation of the universe that are infinite. They go and they come back. And because we are local, we don't see everything. Therefore, we have a real and the imaginary.
And I would say, I'm going to say,
Mm-hmm.
I can't hear you, Steve.
You're muted, Steve.
I know. Everybody. Okay. So I'm going to say that the reason why the infinity symbol is applicable, another aspect is that because space is curved, it comes back in on itself. So infinity doesn't just go this way forever. It eventually comes back on itself. That's why the figure 8 or the
That's
double cipher.
fascinating.
What's that?
What you just said.
Well, good. I hope it applies. We're going to see if Manu and Fred and Richard agree. But
No,
that's how I see it, is because space is curved, it comes back in on itself. It's a giant torus. And
Is
so
a
the
double,
figure 8.
is a double torus.
It's a double torus.
It's a double torus.
It's
Yes.
not 360, it's 720 degrees, just like an electron
Exactly.
spin. Just
There's the concave
Yeah.
and the convex all the time.
just like an electron.
Yes. And that convex, in relationship to somebody that is outside your system, is concave. Because he sees you, you don't see him. So imagine that you are traveling with photon and you are hitting the earth. What will you see?
Say that again. We're traveling where and we're hitting the Earth?
Incoming photon.
An incoming photon comes to the Earth.
Yes. So what do you see?
Light.
You are on your photon. You are like this. You are seeing down like that.
Yeah, I'm seeing
You're
a reflection of
Yes.
of some quantum entity that's smacking a neuron in my eyeball. And because
Yes.
it's reflecting off my eyeball, I experience light.
So you are having a concave experience.
Okay.
And me, your correspondent, the Earthian, I don't see you. I just feel you after. when you manifest in heat.
Okay.
You've come to me, you focus, you've caused me, you have caused me, you are the sign that has caused me to feel in reality the heat.
The cosine experience.
Yes.
Okay.
And you and me are the whole.
Right on.
Yeah.
The other. We're
Yeah.
the other and the other.
Yeah, the otherness.
The
You and me.
minimum of two in universe.
Yes.
Yeah. Now Fred's gonna, if you're complete and if Lee's complete,
I'm
Fred's gonna-
complete. Yes.
Good. Fred's
That
gonna
was
make.
that was what I tried to.
Well,
Can
we're
we-
not
share.
we're not done with you, Manu. We're not done with you. We're gonna let Fred have his feedback first.
We're not done, no, by far cry. Can we focus on phi and pi and not bring any other concept like infinity, the origin of the symbols, curvature, and all these things, so that we get a clear, finite, final understanding of why we call anything pi and phi, because it doesn't make any sense to me.
Okay.
Except the transcendental and the algebraic numbers, which I understand, but I don't relate them at all to whatever has been said. I would like to have a clear, simple, concise understanding of when we say pi and phi, without having other concepts, because then suddenly there's a boatload of assumptions coming in, and it becomes impossible to unwind. So, Manu, please try again.
Okay. I didn't say
Wait,
pi
wait,
and phi.
let me share my screen because I've
Yeah.
prepared a little drawing.
And then we'll come back to you, Manu, and
Okay.
we'll finish up your thing. Thank you for allowing us to get relating to your share. Go for it, Fred.
Okay. So can we use this, because this is always coming pi and phi from this drawing here,
And may I say that that's what
and I do
Manu
not
was
understand it.
demonstrating in his Dymaxion, I think.
Yeah, but I don't see it in 3D. Sorry about that. It's my own limitation.
I agree with you.
I do not understand 3D. I cannot see it until I play with it with my hands, and
Yeah.
this is not something easy to do on Zoom. So, Manu, please go ahead.
Okay. Talking on this that you share on your screen.
I'm sorry?
Talking of this that you've shared on the screen, right?
You want Manu to describe what he's seeing there, right?
Yes. How does pi and phi come into play?
Okay,
that,
beautiful. I like your stuff. I would like you to send me this screen. And Steve, I would like you to send me your Pyre and Fiery stuff, please. But let me talk of this and you see if it makes sense. I am the dot that are in the middle there. And I'm experiencing something. I'm trying to measure something that happens to me.
So you position yourself at the center of the circle. Is that correct?
Yes.
Okay, thank you.
Okay. And we saw and even demonstrated that the circle is the circle could represent here what Becky called the vector equilibrium, the maximum expansion of my 2D there.
Okay.
Then it would twist into the Icosahedron and taking different forms that are more or less defined by two types of contours, the pentagon or the hexagon, or both superimposed.
Okay.
Because it changes.
Yes, yes.
Okay. Now, whatever is inside that thing, that my scope, inside
what? Inside what? Because if it's
okay,
inside the circle,
the
everything is
first,
inside the circle.
okay. So if I'm at the middle there, and I have that, just consider pieces, the contour that is made of pieces of the octagon and the hexagon. Do you see that?
In other words, Manu, may I just interpret you? You're saying I'm the dot in the center and I'm looking out. And what I see is I see this red boundary, then I see this yellow boundary, then I see the red boundary, then the yellow
Exactly.
boundary, then the red boundary, the yellow, and the red and the yellow.
Yeah, yeah.
So I'm seeing parts of the pentagon and parts of the hexagon.
Okay. So what is translate in the first is the pulsative nature of whatever I see. It goes from one to the other. But let's come to the I'm trying to apprehend what is surrounding me. That is what that is in that alternative of red and yellow. I can calculate it easily. I can feel it. I can even see it. That is part one.
And I'm going to just
What are you calculating?
Yeah, you from this little center point, Manu, you're stating you can calculate the red and the yellow and the red and the yellow because you're inside and you can use some logarithm to calculate those.
Yes, I can calculate them.
And when you said you want to be aware of everything going around you, at that point you wanted to become aware of the isotropic vector matrix, which is this sphere. And there are things outside of what you can see. And now we have a problem of how we calculate or how do we experience these things.
Okay,
right?
So let's see. Everything that you see there is in contour an alternate of gold and orange. Do you see that?
Okay.
Everything in the polygon. So that inside part is what I call a leaf, is the air that I breathe. Now, I consider, if you take this.
Sorry, what was that sentence?
I say that
the air you can breathe.
Everything that is, if I share a light inside, to lit inside, and I had two boundaries that are expanding and things, what is inside of the red and the gold at the same time, I would say that it will be evident to me.
Will be?
Evident. Not yet.
It'd be evident. It'd be evident to
me. Okay, thank you. Okay.
Now,
thank you.
Yeah. Now, what is in those triangles that you see there? The
These
triangles that are made of the red and the gold.
This triangle here, that one here.
Yes. That one there.
Okay.
That one there. Yes.
Those triangles. Yes.
Yes. They are a little bit more difficult for me to apprehend, but they're still in the concave stuff on my space. That I know that is a solution to a polynomial equation.
Yes.
In the expression of whatever I'm measuring there, there's going to be a phi. I can approach it, it can be complicated, whatever, but I know that with computation, I can get to it. It's going to converge to something. Whatever I'm calculating.
You mean it's going to converge to phi?
No, there's going to be a phi. You know, the phi is by definition, natural fact, is a polynomial equation, the solution to a polynomial equation. The conversion.
Okay, so let's be more precise, because I believe that's where I have a problem with the wording of things. Do you mean those triangles, whatever you measure within them, will be the solution to a polynomial equation? I agree with that. And therefore, there will be algebraic expressions.
Yes. And I call it fiery. I didn't say phi.
Oh, you said phi, but let's say that's a shortcut in language. Hold on, let's be precise on the language here. And you're saying because they're algebraic expression, they are similar to phi expression. Is that what you're saying? They're not equal to phi, they're not converging to phi, but they are algebraic expressions, as phi is also an algebraic expression. Is that correct?
No, no, that's not what I say. Let me say it clearly. I say that in the calculation of these areas, and it's demonstrable, I can demonstrate it mathematically, there will be usage of phi in the expression. And I've defined it, and I've called it fiery. I say fiery.
Fiery.
Okay.
May
Okay,
I?
I'd be very interested.
Let me just
I'm
say-
very
It
interested
is,
into
it
the
is, it is,
demonstration
it is
that
my
phi
coin. It is
appears.
my coin.
I'm very interested in the mathematical demonstration that phi appears in the calculation of those surfaces there. This,
Okay,
Okay.
and
is
you're
really
calling it
something I would like.
fiery. You're calling it fiery, PHIRY, just like livingry, and just like weaponry, livingry, and you're calling it fiery.
Actually, I've coined two words, either fiery, as you say, or fiery, like
Yeah.
area.
Okay.
Okay. So that's what I mean topologically there. Second thing that you have, if you still take that circle, and then you take whatever is outside of those triangles
Here,
by the circle,
this
that
area,
is still, yes, that
this
is still,
here,
yes,
this here, that
yes,
here, that
yes.
one here. Okay, thank you.
That's still my boundary, because all of that band around it, I call it my boundary. It might be a zigzag or whatever.
Okay,
And I cannot,
and by analogy, this is not the result of polynomial equation because the circle
and I
is.
cannot calculate it.
Okay, got it. I understand it.
Yes.
Thank you.
If heat comes here, I cannot calculate it.
I understand it. And then pi
Okay.
will appear because it's leaning against the circle, so pi will of course appear there.
Yeah. I also call it, I didn't say pi.
I'm very much interested in the mathematical demonstration that, or an example that shows me how and where phi appears in those triangles. Other than that, I've understood what you want to say there.
Okay, but I have a question.
Until I see this mathematical demonstration, I have a doubt that phi will appear. But if you can show it to me, I'll take it.
Good.
Thank you, Manu. That was very helpful. Sorry, Steve, your turn.
No, listen, don't be sorry, Fred, because I think you're doing a lot to mash out, to mesh through and identify the exact equations that Manu seems to be seeing just naturally, just the way he looks at the universe. This is why I call his brain topological. So I love the idea, and I'm seeing some differences in the example I put up of that circle from cosmometry, but I'm clear with you that this area, I can't. Fred, if you would go back and point, the area around the circle outside, that area and that little area up north, a little closer, that little guy and that one. Those are phi calculations in Manu's reference. Is that correct, Manu?
Phi.
Yeah, that you don't. I don't even calculate it. I just say
calculate
that.
It.
Yes, it's convex.
It's convex, and therefore it's fiery or phi area.
Yeah.
Okay.
Is a pyre, yes, because the reality is that if, for example, air, heat is coming from cosmos and hitting my little Earth there, some of that heat is going to come into my air, my space, which I can account for. The other one, I just know that it hit and went.
Yeah.
Who calculated that? And for the practical thing, and let me show you something here. If let's just say I go from the south, do you see my cursor here?
No.
No, we don't see your cursor on my drawing.
So Fred's going to move his cursor down to South Pole.
Yeah.
Okay.
Down there, right? Let Fred be your hands. Fred will be your hands.
Okay,
so
Fred, go right along the goal.
Around the gold.
The goal line.
Okay.
Go right. Stop there. Stop. No. Just stop at the first intersection. You are there.
Yes.
That is one dimension. Do you agree with me?
What is one dimension?
Yeah, that is linear. That's one segment straight.
Let's be precise. It's a measurable dimension. This is not dimension like in 1D, 2D, 3D.
No, hold on. Let me come to something. If you take now a kink onto the red, outward, you've made an angle, you've made a curvature, right? It becomes 2. If you were measuring like whatever that if you had a variable that you had, that variable will now be x squared. It will have a component of x squared. Now, if you
Yes.
turn again, I'm taking yes, there is x3. That's the component of it. If you turn whatever until you come back, when you come back to that point at the bottom there, you have closed the domain with expressions that are weighted of polynomial of higher orders and higher orders. In this case, there'll be 1, 2, 3, 4, 5, 6, 7, 8.
Wait a minute. What are you
9.
counting? What are you counting?
The kings. Wherever you have the kings to go around the goal, yes.
In other words, you're in the middle and you're counting out here, or are we outside here with Fred? Let
No,
Fred
I
be your
started-
hands.
Okay, where Fred started,
Yeah.
you can't, you go there, you go first, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Go down on the goal, on the goal.
The gold. Okay.
Yes. 10, 11, 12, 13, 14, 15, 16, 17, 18. This, you've gone and come back to the same point. That is, the whole total of it is 0.
Total of what? Total
Or
of
whatever. Of me, my experience is that I've not moved. I've gone and come back to the same position. So if I take the kink, those kink, 18 that I measure as powers of whatever variable, with summation of that is add one adding to the other, I'm going to have 0. And because it is finite, there is a solution. That contour is finite. It's a concave, complete contour. So I'm going to find the area inside here. And it is the definition of the phi.
Okay.
The area inside the 18 points that,
Yes.
Good.
let me just finish my statement. The area within the 18 points that Fred just transcribed is definable, is what you're saying.
Yes.
Okay.
And
Yes, you
if I
can
take
take-
if I
Inside it's
take
a
that,
sol-
yes, if I take that area and then I take out the one that it was evident to me, that is inside. So I'm left with whatever is in between the goals, closed by the goal and the thing. And that is
Okay.
part of my boundary that is measurable. That is the measurable side of my boundary. So when you take yes.
I say, why do you need 18th power when you can calculate that in second power without going
No.
any further?
No, I'm just saying, the phenomenon that we use can be many polyhedra. I just took an example. This was just a simple example to illustrate it. Look, I'm looking at the topology here.
Okay.
I'm not particular. I'm not.
Okay.
I'm
got
not.
it.
I'm not fixing. Yes.
I understand it. Then it's variable because if I rotate one of the 2 polygons just a little bit, then instead of 18, I get 20 points, 20 kinks.
Yes, but that's life. That's what we experience. Because the boundary is like this. and Steve, see,
Let's stay in 2D with that drawing before we go
yeah,
to life and whatever else.
yeah, but I'm
Because
just saying the example that Steve has always used.
immediately it becomes loaded with assumptions and too complicated for my limited brain capacity.
No,
Okay, I understand what you say.
I wanted to finish.
I understand. Hold on. I understand what you say. I'm satisfied on the first level of my question, which was understanding where does phi and pi come in this domain. I'm still blocked on the appearance of phi in those calculations, but somehow at some moment you will satisfy me with providing a mathematical example, at least, maybe a proof, but at least an example of how phi appears in those calculations, and I'll be very happy with that. Okay, I'm complete on that. This we can move on unless
Okay, but
unless we want to dive deeper on that.
I'm going to dive
No, I
a
just
little
wanted
deeper.
to give. Hold on, Steve.
Let's
I
finish.
just wanted. I wanted
go
to
ahead.
just add. Yes, to
Go
just
ahead.
add. Take an example that Steve always uses. That
Okay.
is that would be clarifying. Measuring the length of a coastline. You remember that example?
You betcha. Measuring the length of a coastline and the whole concept of the that guy from IBM, not the Julia set, but the I think it starts with a B.
Okay, but that is the point. The point is you can simply measure the distance, that is the flight between point A and point 2 on the coastline.
So I just remembered it. It's the Mandelbrot set. The Mandelbrot set uses to explain how geography or map making is affected by using smaller and smaller units of measure. Okay. Now I got that far. Now restate your statement based on that.
Example, to calculate, if you use smaller and smaller and smaller on the scale,
right?
What are you doing? You are introducing your unit to the power of whatever.
Right.
And then it's getting longer and longer.
Yes, and calculating that y can be orders of difference. You can calculate one mile, whereas is it in actual, 10 miles or 100 miles. You agree with me?
Yeah, depending on the size of the scale you're using to measure the coastline. Because the smaller your measure of scale, please put that back up, Fred. I have more to say about that guy. So the smaller unit of measure, the more you will see. If I'm using a 10-mile ruler to measure the coastline, I'm not going to see the bay. And when I get a 1-mile ruler and I see the bay, suddenly instead of skipping the bay, I'm going to go around that bay with a few of my 1-mile rulers, and I'm going to see more length than I would otherwise. This is the critical element of the Mandelbrot set and the idea of the way fractals relate to themselves by using smaller and smaller measure.
That's exactly what we're talking about, Steve.
Good.
That is a powerful illustration of it.
Okay.
But please understand that when I'm talking, I don't want to be stuck into what I present. Yes.
To keep
that caveat, I think that I have to always precise it at the beginning or whatever I'm saying.
Well, this is a different, for me.
Keep it, Steve.
Go ahead, Manu. Go ahead, Fred.
Just a small remark there. We don't need to complicate things and go to fractal there. What we're talking about is infinitesimals, which was way 400 years before fractals. It's Newton.
Okay.
It's integrals. It's the way of dividing a domain into smaller and smaller parts in order to be able to add up those parts back
the idea is I never reach point B because I'm always subtracting. I'm going at one half, so I never get there. Right?
Okay.
That's Zeno. That's 2,000 years ago, this one.
Right. So, but that's the same principle. We don't need to go to fractals. We can use simple division is what you're saying, right? Fred?
That's what I'm saying.
Okay, good. See, I heard you. That's nice to say. Okay, now I'm going to come back first of all and say hello to Anne, who dropped into the middle of this. Anne, how are you feeling? And are you even able to breathe at this point?
Yeah. I'm good. I'm good. Thank you. I'm so glad to be here. Yes, I'm in and out a lot because this is the first month of the school year, and so a lot of things are happening. And we've got a couple of visitors coming over, the big one. So it kind of, yeah. So thank you for being patient with me, and I'm glad to be here. And this whole thing with what this Manu is explaining, and I'm so thankful, Steve, you and Fred are getting clarification with Manu. So thank you very much, because you're asking the right questions that we would never have even thought of asking. Thank you.
Well, good. So thank you, and we're just delighted you made it, and we're glad you're a grandma, and we're glad you're a participant in our call as well. So thank you for staying busy in your life. Fred, you want to throw that thing back up there? Because,
Sure.
Okay, what do we call this thing? A circle with a pentagon and a hexagon in it. Is there a name for this?
Icosahedron.
Oh.
I guess from one frame of reference,
It's all of this.
Okay, whoops.
It depends on how you look at this.
Yeah, depending. Now, and this is what I'm going to say. You just, when Fred went around the outside of this thing, he came up with 18 sides, an 18-sided polyhedron, because he rotated between the gold and the red and went around the outside of it. And then Fred pointed out that if he shifted the pole on the hexagon just slightly, he'd end up with 20 sides. Is that what you said, Fred?
This would, this here would move until, and you can rotate it until two other vertices coincide, and then you're back to 18.
And then you're back to 18. If you all get that. In other words, if you take the yellow or the gold hexagon and you move it just slightly, and so that over here on the left or on the right, the gold and the red vertices do not coincide. Anytime in between there, you're adding two more vectors, two more sides to it. So you go from an 18-sided polygon to a 20-sided polygon. And then as soon as those vectors coincide at any one point again, which will be very soon, bam, you're back to 18. And then if you keep rotating that hexagon, you go to 20, et cetera, and so on, right?
Yeah. And the enjoyment of life is the watching and the interacting with that movie. Because it's a play.
Yeah.
It is always doing something, changing.
Yeah.
And you see that's what we are, because we are in something finite.
Wonderful.
But something finite that is interacting with other things beyond it.
Okay,
and
good.
Those things create.
I disagree with that. I disagree with that.
Yeah, but this is philosophical now.
I know.
I'll take it out.
The study of geometry is a study of invariance, things that do not change. So the enjoyment of life is finding all those things that never change.
Agree. That's great.
But then we go to topology, which is what Manu's brain is all about, and suddenly donuts become coffee cups and things turn to shit right in our hands, right? Everything we thought we understood about a donut suddenly becomes a coffee cup, and I'm totally screwed up for a while till I get my brain wrapped around that.
But the universe is invariant.
Try the topology of a t-shirt.
Say, what's that, Fred?
I said, try the topology of a t-shirt, because that has more holes.
That's 4 holes. Believe me, a 3-hole. Oh, it has 4 holes, doesn't it? No, it has. Anyway,
I think
we'll talk about it.
You need to count those holes in private.
Okay, good. I'll count them in private. And
we have 4 holes. We have 4 holes.
Good. Okay, but let's leave the t-shirt behind right now, because I want to understand what we have right in front of us.
1, 2, 3, and then my skin is a hole.
Well, your mouth is also a hole, and your anus is a hole. So actually,
exactly.
You're just like you and I are just like a t-shirt. So, but that's I haven't thought of that before, but Joe's having a good time with it. I'm going to make sure that just like a donut and a coffee cup, we've got a human being in a t-shirt.
I will object with
Oh.
that. I think you're more like a Taurus.
Okay. Let's read a little bit. Or Steve, you present what you had to present.
But hang on, because I have some more observations about this figure right here. When I calculated the inside, so now I'm inside, back in the inside, and I'm calculating the sides, I suddenly get a 9-sided thing. So Fred, do you want to start at the top and let's stay on the inside and let's make sure there are 9 sides to that polygon? Fred, if you'll put
Yep.
your cursor on one of the poles, and good. Let's go
Okay.
for it. Okay, 1, 2, okay, 3, 4, 5, 6, 7, 8, 9. Okay, so I looked it up in the Google, and a 9-sided polyhedron is a nonahedron, or it's something more common, an enneahedron, which I couldn't even say. I'd have to look up how to do it, but it definitely is a Nona hedron, nonahedron.
Yes.
Okay, good. So it has 9 parts. So while Manu is out there calculating 18 and Fred's showing how easily it could be 20, I'm stuck inside with 9 of them suckers. And suddenly I realized exactly what Manu was showing us when he took his 3D icosahedron and was trying to show me the hexagon and the pentagon. He had to smash that thing into a 2D plane, and it was a little bit weird, but now I see, if I understand it correctly, Manu, that is exactly what you were showing us with your icosahedron when you were doing the 2 boundaries.
Yes. And you also see that you being at the center there, the 9, the area of a 9 is 9 triangle, is evident for calculating the area of it, the area of it.
Yeah.
It's just
Yeah,
triangles.
we
It's
could
just
come
9
out.
triangles from the
Right,
same
we
point.
could take right from the center point here. We could set out radii that connected with each of the vertices of the 9 triangles.
Yeah,
And
and
then
we just calculate
we
the
calculate
area
the
of a
area
triangle
of
is
each
easy.
one of those 9 triangles, and we'd have the area inside of our nonahedron.
Yes. And I call it, that's what I see. That's
Well,
what I feel.
now, Fred, you're going to the out, but see, I can't see that one, Fred. I can't see that guy down at the bottom. The only ones I see are the 9 on the inside because I'm concave in the middle there. And then when
Yes.
you go
Okay, got it.
outside when you go
I
out to
understand.
this, go ahead. Okay, good.
So
Yeah,
that
so there's
triangle
some
here,
triangles, right?
that triangle here,
Yeah.
Uh,
However,
but
we could also calculate.
that triangle here.
Another point important here is that even the boundary does not escape what I call the duality. Because
Okay,
if you take the boundary the way I've said there,
yeah.
you're gonna see that it's always like 2 colors.
Okay.
Yeah, it always have inside out, inside out, inside out.
Okay.
Except
I'm
here,
not sure.
except when except when you have 2 vertices that coincide, and then you do not have this alternate.
Exactly.
Yes.
Now, I think to help Anne, she's off the thing, but to help me and all of us here, and maybe Anne can see it too, at least when they're watching the recording, if you stop sharing, Fred, and then you held up your icosahedron, we would see, Manu, hold up that icosahedron again with your boundaries on it. I'm going to pin you up here, even though it doesn't do anybody else any good. It
I
does
have
me
it
good.
in the pictures.
Right.
The pictures
Yeah, show
if
the
I share
Yes,
if I share my screen, the pictures
Okay, share
is
your
better.
screen. That's perfect. Share your screen. The pictures are good.
Yeah.
And basically, Manu is showing us the same diagram that Fred showed us, but but this shows us from a 3D context. So we have to mash it down to 2D, and then we see Fred's thing.
Yeah.
Right? Yeah.
Yeah. And even in 3D, we don't see it completely. And that is
Right.
actually the fact. Because if you look at the one that I have now, the one that is in between my hand, My two fingers.
Yeah.
That part you see, but the one, the other side, you just see partially because it
Right.
goes behind.
Right.
Right.
It becomes very topological.
Yeah. You see that?
Yeah.
All of these are experiences of somebody observing. Because we see in 3D, we only see partially.
Yeah.
Only
Well, I'm
see
gonna.
partially.
What's that?
I say we only see partially.
Right.
Our experience in Bucky says it, they are always partially overlapping. You remember that
Right.
expression? Because we are movie watchers as observers.
Yeah, this is a good example of partially
that is.
overlapping this 2D.
It's a good example of
that's
what,
actually-
This
Fred?
2D projection of a hexagon and pentagon. Partially overlapping, yes.
Yeah,
Yeah.
partially overlapping. Right.
So we have the inside that you made me go around, Steve, just
Right.
recently, and that's completely overlapping.
Right.
And then there's the triangles outside, which are which are non-overlapping. And
Yeah.
then we have the pyre, which is not covered by any of those shapes.
Okay, now, Manu, let's get clear on this. When you said, are you saying fiery, P-H-I, re, or are you saying pyre, P-I, re?
He says
I,
both.
I use I use two words. The
Aha.
one fiery, P-H-I-A-R-Y.
Aha.
I wrote it down in the chat already.
Yeah.
Oh, did you? Because
And then pyre, P-I-A-R-Y.
okay, I'm
Those are
gonna.
the two words. Those
Okay.
are the two words that are coined. Yes.
Okay, good. And Fred, as
Yes.
cool as those arrows are in your, I've gotten around it anyway. Those arrows, Zoom does not, or let me see. YouTube does not like those arrows to be pasted into their description. So what I'm doing now, you guys, is I'm going ahead and saving all of the chat out as a Google Doc, and I'm sticking the Google Doc link in everything, in the invitation that goes out and in the thing. So I don't have to go through and change those arrows. And that took me a while to resolve, but I'm happy with it now, Fred. So keep doing what you're doing. The arrows are cool. And Joe just put some damn arrows in there too. So you're both culprits, but now I'm resolving the issue with the arrows. So that's cool.
What
All right. So
arrows?
what's that?
What arrows? I don't see any arrows.
If you look at Joe's sharing there, he says it's the shape of recursion. He says birth, arrow, death, arrow, rebirth, right?
Oh, okay, those arrows. Okay, I was
Those
looking.
arrows, I'll tell you.
I was looking at the drawings. Okay.
Right, right. Well, YouTube hates those damn arrows. And so what I'm doing now is I'm saving the chat out to a Google Doc, and it'll survive that. And I don't have to spend a time editing it. I'm excited about that. Okay, good. So Anne, do you see how this what the slide that Manu is showing right now is the icosahedron? It's the Dymaxion map, which is an icosahedron, and Manu is wrapping the different shapes of the tetrahedron and the hexagon. I'm sorry, the pentagon and the hexagon, showing us these different boundaries, and that those boundaries are exactly the ones that Fred showed in his 2D drawing. And they're much harder to see for me in 3D with Manu's, but now that I'm seeing both, I get it. And so, and I hope that was helpful in there. Okay, Richard has his hand up, and I think I'm complete. Did you have a share, Anne? Did you want to say something?
Yeah, I said absolutely. Thank you. Very clear, very clear.
Okay, very good. Okay, Richard.
Well, I'm looking at something here. When we're looking at the two-dimensional with the yellow and the
Red,
the orange.
Yeah.
And if I heard it correctly, that you can calculate the area that covers the phi area, but you can't calculate the pi area in there.
Fred, do you want to
And
show
then, you know,
your?
just hang on. So then when I see the three-dimensional one that's on the screen,
Okay.
the icosahedron, I know it has 12 pentagons and 20 hexagons, but even visually, when I look at it, it approximates a sphere, but it is not a sphere. I think Bucky chose that in part because it was the closest approximation to a sphere at that time. And so you have to imagine the sphere, and perhaps that's why that part can't be measured. Is that, um, if I'm following it correct, that you can measure the area inside the phi, but not inside uh, the pi area.
Yes. The reason is that anything related to circles or spheres, which are circles in higher
Mm-hmm.
dimension, is based on the ratio of the diameter against the circumference. And this ratio is transcendental. That means you can never know it exactly.
Right.
It's an infinite series of, not series, it's an infinite sequence of digits after the decimal point.
Right.
That's, you can get a very close approximation, but you can never know it exactly. And that
And
bothers
that's why when Bucky laid down the icosahedron to be able to overlay the um, the ocean land configurations of a map, his argument, and apparent, I think it's true, but his argument was that he had the closest approximation of the real world, but not the exact not the exact um, sort of picture of the world. But he minimized the distortions, and the distortion that's on the Mercator map is really quite visible.
Yes.
And yet, any one of us who went through our school years of seeing the Mercator map, no one helped us challenge the size of Greenland, for example.
Yes.
We just began to perceptually assume that Greenland is as big as it is on the map. But when you see it on the icosahedron map, then you see it much, much closer to its relative size in relation to everything else.
Yes.
Have I got that sort of?
Yes, you got it correct. There's two things in my understanding of what Bucky says about approximations of spheres. The first one is that he claims that the usual maps, which are Mercator projections, which are also offset to show the northern hemisphere in more detail, gives the wrong idea about distances and sizes of continents and countries. So that's one thing. The second thing Bucky talks about is a subdivision of a sphere, of the surface of a sphere. And he says, and I think he's correct, there does not exist a scalable subdivision of a sphere in equal dimension, in equal shapes that fits on an entire sphere. There's always a moment where things don't fit anymore. And there's books and papers have been written on subdivision of spheres, and that's also something Coxeter, his geometer's acolyte, talked about a lot. So that was the subdivision of spheres, as same as a close packing of spheres. That was something that was really a hot topic in the 50s, 60s, probably due to nuclear energy development, where in order to get critical mass in a smaller mass as possible, you have to pack as much as possible of this radioactive reactive element. So that's those two aspects. that Bucky.
It's Steve, please keep that map on, please. I just would like to make 2 comments.
Richard, does that answer your question?
Richard, are you complete?
Yes, I'm complete in that sense, and I've got a better understanding of what's not sort of, if you want, measurable in respect to a circle or a sphere. The other thing that just one last thing, in terms of when we were talking about the measurement, if you use, a 1 mile measurement or a half-inch measurement, you get a different sort of solution or outcome. But also, it applies in terms of your position. So if I'm far away from the geography of the land, I see it in a round circle. I see it with a smooth boundary. And the more I come closer to it, the more I see the jaggedness, if you want, in the boundary. And I keep getting closer and closer and closer. And the length of the boundary, if you want, gets longer and longer and longer if I was trying to measure it. Is that correct in terms of
Yes.
not only is it the measuring stick that you might use, but it also has to do with where you are positioned in relation to something. So it's just like if I'm standing a long ways away from somebody, I see the fullness or the wholeness of the human body that you occupy. If I get closer and closer, I begin to see all of the flaws and the changes and the more
Yes.
closely sort of observed differences.
All the rugosity and yes, this is completely correct. And the distance, what you express as a distance from one point to another for the observer, it's very similar to fractal self-similarity at different scales. So what you say is entirely correct. Interestingly, that's a little bit of trivia here. The word fractal does not appear once in synergetics.
That is interesting.
Yeah, that is very interesting, yes.
Which boggleth my mind, actually.
Can I go on?
It's I think it's a matter of popularity. Fractals were discovered in 1961 or 2 by Mandelbrot, working at Benoit Mandelbrot. That's why you say B earlier. In working at IBM in at that moment, 1960s something, but it became popular around 1978 with popular mechanics and all these vulgarization of mathematics journals that started work on that. And Bucky died in 1983, and I think he did not have the ability or the access to that. He could not, even he had access, he did not include it in his work. And Coxeter the same. Coxeter is an old school geometer, and I think by the time fractals came in, he was too old to get into that. That's
good. That's good perspective.
Manu,
Fred,
please go ahead.
Okay. I just wanted to come back to Richard. Keep this map, right? You see where I am?
Yeah, I see where you are.
You're almost off the edge, Manu.
Yes.
I'm afraid for you. Come off the edge.
Okay. I have many experiences in the same day from where I am. I can see the moon crescent and the full moon in the space of 4 hours.
Really?
Yes.
Because you're that low on the hemisphere. What
Okay.
meridian? What meridian
How
are
is-
you at?
How is that possible?
But I'm just saying what I experienced here. I don't know. Fred, you should visit Cape Town. But
How is
you
that
can
possible?
look. I'm where I am here now.
Yes.
I'm on the
Today,
Atlantic.
the full moon. Today, the full moon.
Yeah. I'm on the Atlantic coast here,
Yeah.
and 30 kilometers from here is the Indian Ocean.
Yes.
Not 30, but 50 from here.
Yes.
If I just go south that way.
Yeah.
But that's my experience. But coming to Richard, from Cape Town, let's just say that my experience of a moon is a crescent. Does it mean that the moon is a crescent? Or is it a different thing?
I think
Or
we
is
all
it
agree
that,
it's different.
oh yeah, or is it that I interpret like the full moon is something different from the crescent moon? How you get where I'm going to now here? The observance is very important. The point of the observer. So in that thing that we were showing, the pentagon, hexagon, and changing, and all of the infinitesimal, they translate the continual change of our perceptions. Unfortunately, if you look at this map, it's a very dangerous map to the world order. This map shows that Europe doesn't exist.
What?
Barely.
Europe is Asia
Yeah.
by definition. It's an
Well-
appendix of Asia. Europe is not a continent. Yet, Europe pulls, I don't know how much power.
You mean Europe is part of Russia?
Whatever. I'm just saying it's a dangerous map like this
Yeah.
to the world order.
Yeah. The other map is much
And
safer
you-
for imperialism. Yeah.
But it's not. I'm not talking about politics here. No, I'm just talking about fact and the perception. You see how actually real knowledge, which is this, is different from what shaped our world today.
Yeah.
We go to war for unimportant things. We kill, we maim, we do things.
If
And
you look
and
at-
coming
you
to
look-
Richard. Yes.
Yes, go ahead. I thought you were done. Sorry about that.
No, those were my 2 points. I just wanted to put some fun into our discussion. It was becoming too serious. Okay.
Okay, let me comment before you put some fun into it. First is, if we look at where Iran is, and we can see Africa, Saudi Arabia, and Iran is just there. And if you look at Iran in perspective from China, this is all the road access to Saudi Arabia and Africa. And that is one of the reasons, I mean, outside of there's oil, and Trump doesn't like the clerics over there. That's one of the reasons the neocons are so interested into creating trouble there, because this isolates China. That's one of the reasons. Second thing is on this map, we can see the relative size of Greenland compared to other countries. And that corrects the perception of the Mercator. And my third remark there is that Bucky was justified into introducing this map to correct the perception of relative size of countries, but he introduced distortion in the distances between places. That's all I wanted to say.
But question, who is in the northern hemisphere here?
What?
Who is in the northern hemisphere? Is it me or Steve?
It depends on where your satellite is and where you're looking at the planet.
No, I'm saying to this map, it looks like I'm in the northern hemisphere.
Oh yeah.
And I look like, yeah, it look like the other person, the only person that is invariant here is Anne on the equator. And that we swap everything. It's very interesting, isn't it?
It's really interesting.
No, well, I don't understand why you say you look like you're in the northern hemisphere.
Oh, I'm looking at the map.
It's
Yeah, I
It's
because
on
know you're
top.
looking at the map.
It's on top.
it's because
I'm
traditionally
just
mapped oriented with the north
So all you
being
have to do is
south.
turn the map.
Yes.
no, I don't
And
want to turn. No,
well,
this is just fun. All right.
You know
yeah,
what?
well, you have to understand north and south. It's like if you want to know how far apart I am hour-wise, you can see it fairly quickly if you can spot where Calgary is, and then you draw a line straight across the pole to Mumbai in India. And if you look at the time difference, it's about 12 and a half hours. So we're almost halfway around the world from each other. And then we could figure out, where's Cape Town in terms of the hour difference. And we'll find, we could find out whether it's, 15 hours or 16 hours and it's, I always, this was my point when I was in India. And this may speak to Anne as well. I couldn't understand why Indian people referred to themselves as East Indians.
Yeah.
And of course it's because they're measured from the what's the right word, um, the time zone in England.
Yeah.
The Greenwich Meridian.
Yeah, the Greenwich, that's what I'm trying to say. And so I kept saying, why aren't you willing to tell the empire in that sense to go to hell? We're Asians, or we're Indians. We're not East Indians. We're not South Indians. We're not North Indians. We're Indians. And we live in India. And yet we're so schooled to think of Greenwich as being sort of the center of the universe, I guess, or the empire, and we won't give up our identities that grew out of that particular kind of era. Yeah, and it also shows that if I want to go from Calgary to Mumbai, I have to fly north to the North Pole and then south to Mumbai. And if I want to go from Mumbai to Calgary, I have to do the same thing. I have to fly north from Mumbai to the North Pole and then south to Calgary. The same directions. Yeah.
So this is your point that the India Indians should be called the South Indians.
Well, they call themselves Bharat.
It's tough though because these Indians in America
They call
are
themselves
South
what?
Indians too.
What, Frank? Bharat?
Bharat. I'm checking the spelling now.
Yeah, this map is interesting to really ponder. And now look at today's world that's all business. It's all AI chips, robots, and electricity. Solar power or something. And it's redefining these political boundaries that have been so set based on an empire of bombs and war. And now we're moving into a completely different kind of hegemony that's, if I'm saying that right, that's based on, not even based on money, it's based on technology.
It's always been based on technology.
We will see, Steve. All of these things, the angst and the fears and things that we're having, they had been before. If you read old stories,
Sure.
when the automobile was introduced and displaced the buggy, there were same fears, same angst, same kind of turbulences.
Yeah.
So we are not, you know.
And just to bring out a point of information, that little green dot right there, that sucker is Iceland, and this big white thing here is Greenland. The reason why they called Iceland was to keep white people away. And the reason why they called Iceland, this big thing, Greenland, is because they wanted people to come to it.
Really?
It was all
Yeah,
about,
Right.
it was all about, hey, stay away from here, it's Iceland. And if you look at it, relatively speaking, you know, there's very little ice on Iceland, and there's very little green on Greenland.
Yeah, exactly. That's
Yeah, are we, is everybody clear on this map? Shall we put it down and just catch up on where we are? Manu's still got his hand
Yeah.
up, and
No,
gonna
I'm
stop.
down. It's down.
Oh, you're
Yeah.
down now? Okay, good.
Yeah.
I
Well,
see
just-
four. Any
Richard-
comments to bring
Richard
us
has
up to
something
par?
say.
Go ahead.
Well, I also think it's interesting to use that map and then go to what Bucky said in Critical Path about saying, from his perspective and understanding the migratory patterns of the world started in South Asia, not in Africa. And I've always been intrigued with his rationale as to why he thinks that, if you want, human life could have started in the warm waters of the South Asia rather than on the land of Africa. So,
Richard,
see.
there's a little point on that. It is first, let's look at today. All the markers, I say all the markers are in Africa. There's no marker of ancient that has been found outside of Africa. The second thing that Bucky said is that evolution was from corals. And then Bucky was a navigator. Let's not forget it. So he uses his experience to kind of say those things, because what he says is that on the atolls and corals, those guys, they evolve and then they try to reach the continent. But if you look at the paleontological evidence, what you call scientific markers, none has been found. And you find that in genetics, the richest genetics of a Homo to date is in Africa.
Yeah.
Because as you dilute, as you move away, your stock lightens.
Yes.
Okay.
Now-
I agree with
now-
you.
now-
I agree with you.
So
All those
if you
markers
take-
and all the genetics points to
Yes.
starting.
If you take me, a Bantu, and you compare my genetic stock to that of a Khoisan, I'm poorer. Because I'm poorer. Poor.
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 P-O-O-R.
Poor.
Yeah.
Yeah. Because the Bantus, they went north, completely north, and then came back south.
And I'd like to point out, here's the equator, and everything else is above the equator substantially. And 12,000 years ago, we were in an ice age where the Sahara Desert was lush.
Green, yes.
Yeah, it was green and lush, and there is no, I mean, everything above this meridian would have been in ice age. You know, this is where they were beautiful, or anything above this meridian would have been an ice age, and this was a green belt here. So anyway, interesting points. Any other points on this map?
These are not meridians. These are
What are they? Oh yeah, they are
I forget the name.
Capricorn. They're the
Yeah.
what is a
The
Capricorn?
meridians
Yeah.
go from pole to pole.
The meridians are north and south. They're longitude
Right.
lines, right?
Yes.
And so the
They-
latitude lines are what?
yes. And meridians are all great circles.
Latitudes.
Okay.
The meridians are all great circles,
Yeah.
whereas latitude lines, only the equator is a great circle.
Yeah. I said the wrong word. Thank you. And they're
Okay.
latitude lines or
We'll
parallels. They're
we'll
called
correct
parallels.
you as needed.
Yeah. These are parallels. And the meridians go
Parallels, thank
from
you.
pole to pole. Parallels and meridians. They're parallels. Okay, good. Thank you for that correction. I appreciate that very much. Any other comments on this map before we leave it behind? Great. It's time to go home. It's time
And-
for some takeaways.
And again, on this,
Yeah.
here, you see the great circles here, 3 great
Yeah.
circles on this thing. I've shown
they
it
zigzag.
here.
Yeah, they zigzag.
Yes.
And you know what, Manu?
There's
I've
this
got-
one.
I've got my map. I'm going to make it, and I'm going to do a 2D layout of those of your circles, so that I
Yeah.
understand and can understand. I thought Fred's diagram was really illuminating, and your diagram together, this 3D model with the 2D model, was very helpful for me.
Yeah.
Brought
I
it
want Fred to send me, to share with me. Please, Fred, email me your diagram.
It's in the chat. You can copy. You can click on it.
Okay.
And
And
then
then
it's yours.
Steve, send me the one with the toroid, with the
Okay.
two toroid.
the pi phi.
Yes.
Okay, good.
Yeah. Please.
All
It's
right.
quite interesting. I'm never very good at drawing or doing these things.
Well, that was from cosmography. So, Manu, how are you feeling? And what are your, well, let's do it this way. Anne, how are you feeling? And what are your takeaways this evening? Thank you for joining us.
Thank you very much. Okay, every time we meet, there's always something huge to take away from, right? I think that today was the first time I mean, for me, right, to really look at the map. But looking at the map, I've looked at it a number of times, but the discussions that went around it, the Dymaxion map, I think this is the first time where we actually did it in our calls, right? So and then going down the path of what people in India are called and things like that, because for us in Asia, we only know Indians, right? Yeah. So we've never called them East Indians though. So that was something for me to ponder on, because you're right. Where the Greenwich meridian is supposed to be 0, yeah, why should it be there, right? And then the whole world is like separated into west and east based on that. And literally, if you're at any point on Earth, it's like wherever you are, the east and the west should stem from there, right? But we know back then the Native American Indians were red Indians, right? So to us it was Indians and red Indians, but never East Indians. Never imagined, never thought from. We don't come across that. So that was for me a different way of looking at the world. Yeah. I've already pointed out to my team that we really need to relook, especially my school that's we call the Biosphere School, because in order for us to look at how the distribution of resources go, we cannot use the regular maps. We are looking at being more accurate with how we're looking at the Earth, right? So yeah, anytime we talk about the Dymaxion map, I get very excited about it. Thank you. And to get it's just funny to see how from that circle, and then the hexagon and the what's the other one, the octagon, that we got to the Dymaxion map, and the link is just how we segued into that. I thought was beautiful. So thank you very much. And so Joe, how do you feel, and what is your takeaway today?
I mean, I have a couple different takeaways, and I thought that this very helpful for me. That I've been thinking quite a bit about what we're able to see and understand. And what Manu's model actually demonstrates is, how we have a local perspective and what the limits of that local perspective is. And then that will always have the unseen. And by, acknowledging that requires a certain degree of humility. So when we think about things like the icosahedron or the hexagons, or the pentagons, it's the idea that that we can't really fully capture reality based off of our perspectives is really the most important lesson to come out of that, because it requires a certain degree of humility. And so when you draw a boundary, you kind of, draw a boundary with that in mind, that, this idea of perfect knowledge is not necessarily accessible to us. So, and I think that that's actually critical to when it comes to harmony. So it's not about perfection. It's not about absolute knowing. It's about harmony and how do you create that. And so I think what this is the geometric aspects of that. And I think that, what we were fortunate enough to go through is to understand in a very specific way how there are different perspectives, but there's always something left unseen. This was really good for me. I mean, I may not have spoken a lot, but I very much am in tune with what is being said. Just also I'll put something in there in the chat in a moment. I'll keep getting your hexagon, pentagon. I'll put it in there in a minute. I'll have to pull it up here. And it reminded me of the Dymaxion map. So the truncated icosahedron, and it's a soccer ball. And so when you look if you look at that, you can kind of see where the world map comes from. So that was another interesting part. The last thing was, Steve bringing up, I put something in the chat, the video in the chat, regarding clean energy, essentially solar, and how I have to double check these numbers, because if they are real, I mean, they're the most mind-blowing numbers that you'll ever see. I mean, really, if those numbers are absolutely, and there's no reason to believe that they're wrong. And that means that, that has huge implications. That, China's in 1 year puts out what would be equal to half of the entire U.S. Average power, the average power they use per day. They're putting that out each year in solar specifically. I mean, that's mind-blowing. Anyway, so that's something that we don't see over in the United States. But so anyway, and Fred said he's going to give us a new grid. So very much appreciate that, Fred. And so I had a really good time. And again, I think that this is very helpful for me by understanding boundaries and the limitations of knowing in general, because there is definitely, I think sometimes we think we know more than we do. We infer more than we should. That's a better way of saying it. Our inferences are completely unjustified. and rules based. So with that, Lee, how are you feeling?
I'm feeling wonderful. And
Good.
Joe, thank you. What you said at the end, and not being the Italian that wanted to speak continually and interrupt everybody, was amazing, because you brought up a great summary with that football that you diagrammed there or had as an icon. Really made everything come together for the world, as Fred had made, and Manu and Steve and all the others that worked on that map. The map was wonderful, but I liked that football. That is more realistic than the map that I saw of the world. But now I understand that map of the world. Steve has one, and my granddaughter goes to it every single time she comes over here. She loves that map of the world. She loves it and takes it apart, makes bracelets out of it, and just thinks it's the greatest thing ever invented. And I think you need to have it continually in your classes, because a 6-year-old really was in tune to it. And she could put it together, and I could not figure it out at all. I could finally understand what Manu was trying to get to. Manu has language that I do not understand, but he gets in clarity when he sees a big question mark above my head. He says, okay, let me explain it again. And I appreciate that, Manu, because with that diagram that Fred sent us of the pie, or the hexagon and the octagon, I really now understand it. And the phi and the pi, I'm not sure about the pi area or area or whatever it was called. I'm not sure about that yet, but it'll come probably till next year. But I know it'll come in next classes or meetings that we have. To me, it is definitely a class every time I come here. I appreciate being a member of this group of people. And Richard, how's your feeling, and what is your takeaway?
Well, I'm feeling pretty good, and I've actually in connecting with the map that Joe put up was interesting, because it was connecting me again to the discovery of the Buckminster fullerene, or carbon 60, the third form of carbon that up until it was discovered, everybody says there's only 2 forms of carbon. And on the Buckminster Fuller website, writing about some of the big ideas, I was able to write about the beginnings of, or the discovery of, the Buckminster fullerene. And one of the fascinating things about that story is that when they were trying to put together this idea of something that would curl into a full circle or a full sphere, they originally recalled the geodesic dome at Expo 67, and their image was that it was made up of hexagons. And so when they did sort of paper hexagons and tried to put them together, it would never curl because it just rolled out like chicken wire, which of course is made up of nothing but hexagons. And then in the struggles, all of a sudden, I don't know which one of them was, but sort of realized that, wait a minute, that geodesic dome has pentagons as well. And so the mathematician, or no, one of them put together the hexagons and pentagons late at night, and all of a sudden he started to see it curl, and it curled up into a full sphere. But he didn't know what he had. So he sent a message to the mathematician at Rice University, a colleague, and said, I discovered this last night, but I don't know what I have. But I think it's what we're looking for. And the mathematician wrote back something, well, there's a big name for what you've discovered, but if you want to know what you really discovered, you discovered the ordinary soccer ball. and and that's partly why the Buckminster fullerene eventually truncated down to being known as the buckyball. But in the early naming of what we're going to call this fullerene, they suggested football arene, soccer arene, a whole bunch of things, until one of them says, well, look, we got all this idea from Fuller, so let's call it a Buckminster fullerene. That's the correct name. And also the convention, naming convention, says that the discoverers can't have their name attached to whatever they discovered. And so that's another explanation as to why it's a Buckminster fullerene and not the name of one or more of those discoverers. Anyway, so I've always been intrigued with the story of the carbon-60, which is, for our discussion today, it was kind of the reverse of how you put hexagons and pentagons together to get that spherical. In fact, carbon-60 is more spherical than the icosahedron. So it's a little bit more complete in terms of the full sphere. Plus, I'm also interested in this idea of the mystery, this idea of there's always something that can't be fully measured, whether it's in this notion of the sphere. And it always connects me to the idea that both in science, the materialistic science, it tries to solve everything. And in lots of religions, that's the attempt in a religion as well, is to be precise about, if you want, the hierarchy, or and whereas other people, I think, are saying there's a mystery out there. And the mystery could be called a god, it could be called an Allah, it could be called lots of things, but it's the mystery, and we shouldn't try and personify it into a human-like form, which is what we do. So I've always been intrigued with allowing the mystery of the universe to have its place in our attempt to find livery for everybody on this planet. So, Anne, what's your takeaway? And
She went.
oh, sorry, yeah. Where am I at? Fred, how are you feeling? What's your takeaway?
You're muted, Fred.
Sorry, I start again. I'm feeling very grateful to Manu for preparing his explanation from last week's questions. That was really enlightening, and I finally understood something about fiery and pyry. And frankly, it's like clearing. It's removes a lot of confusion and a lot of frustration. And frankly, it's really nice to get to that point. Joe, please check those numbers. This sounds like a lot. Those
Well, that's basically from the video.
okay.
It's from the
Okay.
video.
This really sounds like a lot.
That's from Davos this past week or 2 weeks ago. Those
Okay.
numbers.
Okay.
Yeah.
Well, I don't know. I have not watched the video,
They
but
they sounded crazy to me too.
What's
yes.
from Davos?
So if
The
you look
video that
the
says
video that I put in there, it's
that
essentially
China new construction of solar power
Oh, I
generation
got it. Yeah. Okay, cool.
is larger than is about half of already installed total U.S. electricity consumption.
Yeah.
Okay, never mind. That sounds like a lot. Anyway,
it's great. If it's true, it's crazy.
yes, absolutely. It's a lot, but I'm not sure it's that much. But it's a lot. Even for a Chinese cheerleader like me, it sounds like a lot. So,
That's
um, Manu, I would like at some moment that we went into fiery and had a look at this mathematical example, how we get phi out, how we find phi inside this fiery. I would really much like that. And because it's time and we pass time, that's all my takeaway. The essential of my takeaway is there. Thank you very much. And Steve, how are you feeling today? And what is your takeaway?
Manu gets to go.
Oh, sorry, Manu. How are you feeling? And what is your takeaway today? Sorry about that.
I feel good. I feel alive. And thankful. It was really an interesting conversation today, and I'm really trying to get simple. It's I think I will get there one day, but it's a continuous effort. I take one expression from Richard. I can't remember exactly, but the consequence of it would be summarized like this. I think it's when he was talking about God. Instead of, I think that to be an enjoyer of life, to be a good citizen of this earth, to get rich on this earth, what you have to understand the general principle that hold the whole of this together. And I think it's fundamental. My personal experience is that trying to understand them has rather simplified things for me. And it helped me to be humble when it's needed and to be bold when it's required to. Because you know that there's a chance that it will hold. And then a comment on the solar. And unfortunately, it might be like the other stuff. The largest and by far and the less inhabited desert in the world is in Africa. It's called the Sahara. And Americans will know it very well because, it influenced a lot in North America. And it was pristine and lush at one time. So there's a lot of water that is underneath that stuff. And a deployment of solar, instead of being like China want to do, the US want to do in this, we know that energy is current. That is, the farther you go from the source of it, the lesser you get. let's look at the real way of making this potential wealth beneficiary to humanity. There's got to be a project to sizably cover the Sahara with solar panels and find a way to transport that energy using marine cabling, submarine cabling, to wherever it is used. And that was very well in the spirit of what Becky thought about. And it's possible today.
I've wrote
You see,
I've wrote an article about that in 2009, blog post about covering the Sahara. Actually, you only need a 400 by 400 miles square to cover the total humanity needs of electricity.
Go
So-
ahead, Manu.
yes, so today we have
With solar
the
panels.
technology.
Yeah, I've written.
We have the technology, and we just don't have, like it is the old, how will I call it? Type, Susan will call it type 2. Is it type 1? Type 1?
Type 2 evolution.
Type 2 evolution that prevails.
Yes.
And unfortunately, but that is my hope.
Yeah.
That this will be seen in that light, in the light of the article, the blog that you wrote, and realize and taught. Anne should teach that, because I don't know which powerful leader of this world is going to come out of Anne's school. I don't know.
China is doing it. I've in 2017 I had a road trip on the Qinghai Plateau, which is 3,000 meters high, which is 3,000 meters high. That would be around 9,000 feet, 9,500 feet, and it was solar projects after solar project after solar project on the whole plateau. It was hundreds of kilometers of solar projects, and on the hills was wind projects.
Yeah.
And that was 2017. I've not been there yet, again following that, but I've seen pictures, aerial pictures. It's covered with solar panels and wind farms.
Yeah. And doubling the Sahara is agriculture, because there's water. It's known that there's huge reservoirs of water all across the Sahara. If the Nile can travel the Sahara to the Mediterranean, and survive, it says a lot. So I mean, that's my takeaway. It is possible.
Yeah, we're talking about lag here. We know it's
Yeah.
possible for 50 years, and it's only starting now to take shape.
Yeah, but hoping that we'll get to those things in a majority before we reach doomsday, because
In the nick of time.
where we're going today, we might bomb ourselves out of life
Right.
Yeah,
before we ever reach it.
it's
Okay.
all in critical path. We're going to make it or not make it.
Okay. So that's my takeaway. Yeah. and then without this, actually this forum, I don't think that I will be thinking about these kind of things. So I'm very grateful. Steve, how do you feel? What do you take away?
Okay, well, I'm very grateful for this forum too. And I've cut out my little Dymaxion map, and I'm doing what I can to put it together to resolve a question that I still have from Manu's example. I want to thank Manu for doing his homework, bringing those pictures to the conversation today. And I want to thank Fred for throwing a 2D explanation up of what Manu was trying to show in 3D. Somehow, Manu, your brain is so topological, it doesn't make any difference if it's 2D or 3D. I really appreciated seeing that 3D model squished into 2D, and our discussion about infinities and fractals relative to all this really helped in terms of what was going on. So thank you, Fred. Thank you, Manu. Thank you, Manu, for like initiating and holding true to doing what you can to explain to my brain what the hell you're thinking of. Let me just say that Elon Musk has already purported the idea of somewhere in the what we call the Four Corners area between Arizona and New Mexico, even as far as northern Texas and the Panhandle. We only need 400 square miles of that desert that is not being used, that has no water underneath it, as far as anybody knows. That 400 square miles of panels would serve the US completely. We would need batteries. We would need batteries because it wouldn't store overnight. But if we were using Sahara in nighttime and the Arizona desert in the daytime, we'd be in pretty good shape. Here's what's interesting to me. I love when Anne brought up the biosphere. And, we talk about the Earth, we talk about the map, our geography, our geosphere, but we have a biosphere, which is really profound. And now we have a technosphere going on. I don't know if you guys heard in the last couple of weeks, and I think it was related to Davos, the Davos convention. Elon Musk announced that SpaceX is going to put, over the next 3 years, is going to put all their AI up in outer space. They're going to put it in solar-centric, I forget what the word is called, but they're going to put them in low Earth orbit in a way that each of the satellites will maintain contact with the sun 24/7. And because there's no atmosphere, and because 97% of the AI infrastructure on the Earth is cooling. 97% of the infrastructure required for an AI chip is cooling in outer space. Because there's no atmosphere, the heat just totally dissipates into the vacuum of space, if you want to call it a vacuum of space. And so maintaining AI compute 24/7 in outer space is the way to go. And in 3 years, there'll be so many thousand AI computers roaming around the Earth. Suddenly, it's going to make a major freaking shift in our politics, this technosphere. And because whoever has the AI is going to be kicking butt, either making huge mistakes or making huge progress, or both. And with Elon's plan, within 3 years, they're going to be making satellites on the moon. This is what Elon wants to do, and using electromagnetic slings to throw those AI satellites into space within 3 years. And so we're going to have thousands of AI compute satellites that are 24/7 in contact with the sun. And then all they're doing is they're uploading input and downloading output. And it won't be happening on the Earth. Wow, is that going to change things significantly? So there was that. Fred, 3D, 2D, Anne's comment about biosphere, Manu's explanation. I'm just really excited. I never knew about a nonahedron before, and I certainly didn't know about an 18-sided polygon. I'm going to be looking at that too, and I'm going to be screwing around with this Dymaxion thing to understand exactly what's going on with the circles there. I'm really grateful for this group, and I agree. I wouldn't be having this conversation with anybody. Totally thrilled with what's going on, and so humbled to be here. So grateful that each of you take time to be here and share. Thank you all for your contributions. I'm complete. See you next week, all.
Thank you very
all for
much.
being here. You betcha. Bye-bye.
Yeah, I mean, one of the things, really quick, Fred left. He said, he said about Musk copying, and I said, well, the old Steve Jobs statement, good artists copy, great artists steal. That's, and I still believe in that. So, all right, I'll see you. Take care, everyone.
Bye-bye.
Bye-bye.